Okay, so in this video, we're going to look at the relationship between correlations and scatter plots. And what I've done for this is I've created some simulated data so that I could easily adjust the correlation values. I have some X values that I generated using the ran between function. I generally try to approximate these as essentially ages between, let's say, 0 and 75 or something like that. 0 and 100, and then I created equations. The positive slope equations were based on the equation 1.4x plus 11.1 plus an error term, and the negative equations were basically the same thing, but with a negative slope. I increased the intercept so that all my values didn't end up being negative, but then also an error term. And as we progress through these columns of data, the error increasingly goes up. So all of these up through Y7 are all positive slope examples, but with increasing size of the error as we go. And the negative slope equations start with Y8, and then they decrease the error down to the smallest error that I used in the very final column. So what we expect when we do the scatter plots of these is that we should have a very high correlation, tight to the line, small error in both the first column and the last column. And then in the middle, we should have very poor correlation with possibly having a great deal of difficulty determining the regression trend at all. Now, the size of the error started out with a mean of 0 and a standard deviation of 1 on both extremes. This is representing the residual error essentially, using the normal distribution and the rand function, which I've talked about in other videos. And then I just increase the error. The mean stays 0 in all of these cases, but the size of the error increases from 1 all the way up to 100. And the thing about the 100 is this is a very large error relative to the range of the X and the Y values in particular. After the X has been multiplied by the slope, the standard deviation of 100 means that the error 95% of the time will be between negative 200 and 200. And so that sort of is large enough to sort of overwhelm the change based on the regression, the original underlying regression equation. The idea here, of course, if the Y range is larger based on the regression equation, maybe the slope coefficient is much larger, then the error that you would need to get low correlation would need to be much larger. So it's a relative error that we're talking about. As the relative error increases relative to the range of Y, then you will get lower correlation. So that's what we want to look at. So what I'd like to do first is I'd like to calculate the correlations for each of these relationships, calculate the correlation for each of our Y columns correlated with the X variable that they were all based on. Now, even though I use the rand functions, I pasted these as values, so they're not going to change as I make continuing calculations. So the correlation is calculated from the Correl function. The first column is X, and the second column for our first calculation is V, Y1. Now, again, the error is relatively small compared to the size of the underlying Y range, and so we get a very tight correlation to this example. Now, what I want to do for each of these subsequent ones is I want to just change the column for Y. And again, you can see this is still a pretty high correlation. This is, I think, an error of about 2.5. So it went up, the error size, again, relatively speaking, increased, but it's still relatively small compared to the size of the rest of the data. And so it's still very tight correlation, but it is smaller than it was before. So column 3. And again, we'll see is that until we get to Y7, this will continue to get smaller. Still pretty strong. I think now we're up to about an error of about 10. Actually, what's this one? This one should have been E. Yeah, so this one is about 10. This one is now up to 20 as an error. This one is an error of 50. So now we see that the correlation has started to drop significantly. And then when we do Y7, now we have very, very low correlation. It's actually, when we plot the scatter plot, it may be difficult with a correlation this week to even tell the difference between just random noise and that there's a very slight trend. Now, if we start with the next set of these will have the negative slopes, and so we can expect the correlations to become negative. And this is going to be with Y8. And again, it's still pretty low. It's kind of in a moderate range, but it has now flipped to negative. So what we expect to see when we look at the graph of this, that we will see that there's a trend. It's kind of spread out because the correlation is pretty weak, but we will see a negative trend. And then what we can expect is that the correlation, because the error is going to get smaller now, the correlation is going to get closer to -1 because it's negative, because it's a negative slope, but closer to 1 or -1 is tighter correlation, stronger correlation. Now we're down to about an error size of about 10 again. And we can see that as we continue, the error gets smaller and smaller, getting closer and closer to 1. And we can see that, again, the correlation, similar to what we had at the beginning, is getting very, very close to 1. But as long as there's any error at all, the correlation will not actually be 1. So we can get really close to 1. And again, that error is relative to the size of the range of Y, generally speaking, based on the relationship with the line. So let us now compare these correlations to the scatter plot so that we can see visually how these correlation values can be detected just by looking at the graph itself. So we're going to start with just X and Y1, and we're going to build our scatter plot, and it should come up as the default, and we'll slide these over here. But what you can see is that, again, the graph is very tight to the line. There's a little bit of wobble, but that correlation is almost one. It really fits that line very, very nicely. We don't even really have to impose a trend line on it to see that this is obviously following a straight line. Now, let's look at X and Y2. And we'll pull this over here. We can take a minute to look at it. And again, you can see that it's still following that same trend, but it's a little bit more spread out. And again, it's so tight still. We don't really need to impose a trend line, but it helps to see that little bit of wobble has definitely gotten bigger. The points are still in that general trend, but it's a little bit further from the line. Now let's look at Y3. And we'll see this continue. Let's drag this over to the side. We'll see this trend continue. Again, still that same trend, but now even more spread out from the line. We're still at a very high correlation though. We're still at 0.989. And now we start getting into the errors that are in the double-digit range. And again, they continue to spread out a little bit more, a little bit, fairly slowly. Now, as we start to continue to double and double and double our errors, our scatter plots are going to, again, continue to spread out more and more and more. So now we're at an error size that is as big as 10 or 20, I believe, at this point. 20. And so again, you can start seeing them, again, continuing to spread out. Our correlation is now down to 0.9. It's still very good. There's still a clear trend, but you can see that they are spreading out more and more. If we then make our scatter plot for, this is our error that was about 50. And now we have basically a 0.6 correlation. And the errors are getting much larger relative to the size of the rest of the data. They're getting much more spread out. You can still see this general trend, this positive rate of increase, but now the errors are starting to really kind of eat away at that, our ability to detect that trend line. And then our largest error our Y7. This is the one that has an error that is 100, standard deviation of 100. And as you can see, 100 times 2, again, 95% empirical rule, that is going to give us a very large error relative to the overall range of the original data. And again, we have a hard time here actually sort of seeing that there's a trend at all. very, very slight trend. But we can detect it, even though the correlation value is as low as 0.2. And again, if it's 0, basically you just have all the data in a horizontal box. This one is ever so slightly tilted. Now, if we plot the remaining ones, then we'll see a similar trend in reverse, but the slopes will now be negative. So this is our roughly 60% negative correlation, our 0.58 that we had before. And we'll put these down here. And again, we can see the trend line. This is now negative, but this is very spread out. This is like our positive slope that we had earlier. This one. But now the scatter is in the negative direction. The trend is in the negative direction. That was y8 and we y9. And then as we progress through these, we will see that they will begin to when you grab the graph, and the graph is not cooperating. They will tend to become tighter as we go. Ten. Trend line. Now we'll zoom out once we get all these graphs created so that we can see them all collectively. Y11, and again, we'll expect this to get tighter and tighter. Oops. Okay. One last one. This is virtually one. It's just a very small deviation from perfect. One close our trend line. And then what we'll do now is we're going to back out a little. So we can see all of these together. . So here's all of our graphs. So we have, and again, the text is hard to read so that we can see all of them, but we have our very tight, almost +1 correlations, and they get a little bit looser, a little bit looser, a little bit looser, until we end up with a very difficult to see positive trend. And then our negative trends start with the looser, and then they come together. As the error sizes get smaller, the correlations get tighter and tighter. They get closer and closer in the negative case to -1. The absolute value gets closer to 1. So this is one way of sort of thinking about what does a correlation mean. It's essentially a measurement of this relative size of the error that's included in the data compared to the spread of the trend relationship itself. This is where one of the places where this interpretation of the R² value comes from in terms of the percent of the variability that was explained. So that relative error that is left after you've explained the trend relationship. That's why that correlation is related that way. Now, there is one additional thing that I wanted to do with this example, and that was to create a correlation table for you. Now, a correlation table typically is something that you use when you're doing multiple regression analysis, when you're trying to determine the best set of variables or the best set of variables to use in a multiple regression analysis, and to detect in case there are any collinearity problems within multiple variables. Now, in our case, we would expect the correlations with different variables to be relatively high, since they're all based on the same linear relationship with just this error term included. But the way that we do this calculation is going to be the same, whether it's this kind of simulated different y values based on a single x, or if we have lots of different independent variables based on x. Now, the way that the correlation table is constructed is using the data analysis toolpack. And so if you have that installed, again, this is a free thing that comes with Excel. You just have to turn it on in the options menu. Obviously, other kinds of statistical products will have similar things. And I'm going to select correlation from my table, and my input range is going to be now for the data analysis tool. You can't just highlight the column. You have to actually go all the way down to the bottom of the data. It's grouped by columns. Labels are in the first row. And I'm going to put the output on the same sheet, way over on the. You certainly can put it on a new sheet. With this many variables, the table will be somewhat large. And then, okay. And so what you get, now in this first column, all the y variables correlated with x. These are going to be the same values that we calculated one at a time using the correl function, the correlation function. Same thing. Now, if this entire table was filled out, we would expect complementary values all the way down this row as well. Now, that is why this table is only filled out halfway, because the top half of the table and the bottom half of the table are going to be exactly the same. Now, what this does then is that the rest of the table is going to actually calculate the correlations with all of the other variables. So this entry is calculating the correlation between y1 and y2. And this one is calculating y1 to y3, and y1 to y4, and y1 to y5, and so on and so forth. And you can see that in the middle, where the error was already the highest, these correlations are all pretty low. And they generally get worse as you flip over from the positive slope values to the negative slope values. Again, which is to be expected. Now, because all the negative slope values, they're positively correlated with each other because they're going in the same direction. But the correlations between the positive slopes and the negative slope values are all negative. Now, in a typical independent variable case, you would want to weed out any variables where there were strong correlations, either positive or negative, from your set of multiple variables. So for instance, if these were all different independent variables, or you think they're independent variables, and let's say X5 and X6 have a high correlation between them, when most of the other ones have weak correlations, you would want to weed one of those variables out generally because it's not providing you new additional information. Something that we can think about when we do multiple regression analysis. But this is a nice quick way of getting all of your correlations, even if you only really care about the correlations with X. This is a nice quick way of getting all of your correlations calculated all in one fell swoop.